Okay, I apologize, everyone. My mic setting keeps getting messed up, so I'll just continue. If you guys had questions, you can ask. Alright, and then we talked about antiderivatives. Alright, so we talked about what an antiderivative is, and this is also known as an indefinite integral. Alright, and so this is where we take a function, we modify it so that if you took the derivative of it, you would end up with the original function. And so the antiderivative of sine of x, which is written like this, is essentially what function, if we took its derivative, equals sine of x. So we're essentially asking here, what is f of x? And this is the antiderivative. I'll go over in a second how you sort of figure this out. But for now, let's just think about it. What derivative will give us sine? Well, the derivative of cosine is negative sine. So negative cosine will give us that. And then we also add in this plus c, which is just some arbitrary constant that can be anything. Because if we take this derivative here, we get sine of x plus 0, because the derivative of a constant is 0. Alright, so we talked about the reverse power rule. This is the first, this is as fundamental to definite integrals, or I'm sorry, indefinite integrals, as the power rule is to derivatives. So to integrate something like x to the 16th, we do x plus a over 1, so 16 plus 1, 17, all over a plus 1 plus c. Okay, and that makes sense because if we take this derivative, we get x to the 16th, which is what we're looking for, all over 17, but we remember the power rule. These cancel out, and we're just left with x to the 16th. And then taking the derivative of c is always just 0. Okay. Alright, so this next technique is called rubber banding. And that sort of comes from what we're about to do, is we're going to divide this bottom part out. And the way you do that is you divide these, and then you divide these, and these sort of look like rubber bands. Okay, so we already did that one. Let's do a quick example. So if we rubber band this, we can simplify this to the integral sine of x over sine of x, which is just 1. And then tan of x over sine of x. Remember, tan is sine over cosine. 1 over cosine is just secant. Which brings me to my next point. I'm sorry. Integrals you need to know. So the integral is secant. Without knowing it or doing it by parts, which we'll talk about next week, but only if you're in BC. So the integral of secant is ln absolute value secant x plus tan x. So we can integrate this. Okay. So if we don't have any questions, I can move on. Alright, and this is next to the reverse power rule, probably the second most important thing you need to know. And this is U substitution. If you don't have any questions on that, I can move on. But essentially what you need to do is you need to set U equal to something in this integral. So here, sine squared x. You find what du is in relation to dx, so you're just taking this derivative and this derivative. And then substitute in u in up here, and then dx and for du right there. And what should happen is that terms should cancel, and you should be left with an integral that's only in terms of u. So here if you do it, it's e to the u over 2 du. Now sometimes you'll have to do another substitution, and so in that case what you would do is just say v equals like something like maybe u squared dv equals 2u du, and then again substitute. Alright, so I also talked about polynomial long division. Hey guys, welcome to the LearnAP Chem livestream. Submit your questions in the chat and we will do our best to answer them. For now, sort of my software is still booting, but if you guys have any questions, you can submit them, and then once everything starts to work here, we can get set up. Okay. So I'm just going to change the title real quick. Okay, so Arnold, you had a question that we can sort of talk about now while this gets set up. And that was, why are attractive forces increase when molecules move slower? And so that has to do with actually density. So I assume when you say something moves slower, you mean that it's at a lower temperature. Okay. So you mean that it's at a lower temperature. And it actually doesn't have anything to do with why, with the fact that things are moving slower at a lower temperature. It actually has something to do with density at temperatures. So, if we think about sort of an atom, let's say, or we'll say a compound, we'll say it is in the liquid state, and in one we have them at 0 degrees Celsius and the other at 15. Okay, so you brought up the fact very recently. Why are attractive forces stronger when the particles are moving slower? And so essentially what I think you're asking is why is it stronger at lower temperatures? It actually doesn't have anything to do with the actual motion of the particles themselves, but actually density. So let's take a look at what that looks like. So I assume you're familiar with as we lower temperature, things in general get more dense, but at a higher temperature, things start to spread out. And so at lower temperatures, these atoms are closer together. They're going to feel, let's say maybe we have a positive dipole here, negative here. They're going to feel this attraction much more. And this has to do with Coulomb's law. I don't know how to spell it, but it says that the strength of the attractive force is equal to the charge of one times the charge of the other, all over r squared, which is the distance. So here our r is actually rather small. So this is going to come out to a larger number than over here, where my r is much, much larger. So that's why at lower temperatures the attractive forces increase. And that's because essentially the atoms are closer together, or compounds, and they're going to feel the attractive forces more according to Coulomb's law, which is this. Alright, so hopefully that answered your question. I believe you had a couple others, so let me just get to those real quick. Okay. Okay, so When explaining Graham's law of diffusion, what exactly do you mean by vacuum? Alright, so if you think about, let's say you're standing here on Earth, and there's sort of air all around you, right? Well, in the air it's basically a bunch of particles. We have a bunch of atoms occupying this space. And what it would mean to be a vacuum would mean that in some amount of space, rather than having, say, like oxygen, most of it is nitrogen. I think it's a triple bond. That should be... Alright, I won't worry about correct Lewis structures for now. And so, in some space of air you have nitrogen atoms, oxygen atoms, maybe some carbon dioxide. But in a vacuum, there's nothing. There's no atoms whatsoever. So when we say something is diffusing into a vacuum, that means they're sort of diffusing into something where there's no other gas particles. And so the reason for this is if something is sort of diffusing into something with a bunch of gas, then you have to worry about, well, what pressure are these gases exerting? And AP chemistry just says, assume it's a vacuum, don't worry about it. So the closer they are, the slower they move because it is much more dense. Correct. Yeah, that's exactly right. And then you also asked, on the challenge problem, diffuse would have to change to effuse, correct? Yeah, okay. Yeah, you're right. That's, I don't know, just sort of a typo. Because, you know, do note that diffusion is not the same as effusion. I make this mistake a lot, so just note that. Although, I mean, you're probably not going to be tripped up by it. Okay, so I suppose we can just go over what we talked about last week. So we started with IMFs. Wait, is that right? Yeah. Okay, so no, we did this one. Yeah, I don't know why that gets moved around like that. It's sort of weird. Okay, so we talked about kinetic molecular theory. It sounds complicated, but it really isn't. And this is basically making a bunch of assumptions and about atoms in the gaseous state. So this only applies to gases. And in particular, you're going to see this with gases at low pressure. And high temperature. So let's take to think for a second why we would assume this. And I'll come back to answer that after I sort of walk through these postulates. Alright, so the first is that gases consist of molecules and or atoms moving in random directions. Okay, fair enough. That sort of applies throughout gases. Okay, and so second is that collisions between these molecules and or atoms are perfectly elastic. So what I mean by that is, let's say that this is coming at 4 meters per second, and so is this. The rebound, there's going to be no energy lost. And actually this is nominally true, just because they won't actually collide. They'll essentially get very close to each other and then repel. So this is one of the few perfectly elastic collisions where energy isn't lost to friction. Alright, the third one is that volume occupied is small enough to be negligible. Fourth, the attraction or repulsion is also small enough to be negligible. And finally, the average kinetic energy is directly proportional to the temperature. Okay, right. That's good. Okay, so if we sort of go back to this, that this mainly applies to low pressure, high temperature, we want to think about why that's the case. And to understand that, I'm mainly concerned about these two assumptions right here. Now, at a low pressure and high temperature, my atoms are going to be spread apart. And so in this case, the actual volume here is actually small enough to be negligible, because the volume in comparison to the amount of space is very small. Also, we have a large distance here, so we can assume that these attractive forces are going to be smaller according to Coulomb's law. So that's why this works at low temperature, high pressure. And if you think about it, if we shrink this down to a lower temperature or maybe a higher pressure, where these are going to be closer together, now this volume is important. Now our attraction is not small enough to be negligible. Alright, so Graham's law of diffusion. This one is pretty straightforward. Honestly, I suppose it's just hard to know what VRMS is, and that is the speed of diffusion, which is in moles per second. With low pressure, there's bigger volume. Okay, yeah, so once I answer your question, you can let me know what that is. There's a bigger volume. So does that offset the fact that when atoms are at a higher speed, they hit the walls more and thus higher pressure? So with low pressure, to answer the first part, when there's a lower pressure, that corresponds to a higher volume. So you just remember P1 V1 equals P2 V2. If our pressure goes down, then volume has to go up for this to still be true. So yes. So does that offset the fact that when atoms are at a higher speed, they also hit the walls more, thus a higher pressure? When they're at higher speed, that would imply a higher temperature. And so, yes, you're right in that a higher temperature will correspond to different pressures. That being said, what we're really concerned about is sort of our volume here. And at higher temperatures, gases occupy a higher volume. So if that sort of answered your question, otherwise you can let me know. Or you can just ask me your question about Graham's law. Yeah, so I guess the key here is to memorize the actual formula itself. Because it is sort of tricky. Alright, so average kinetic energy and velocity. Our kinetic energy is given in joules, so KE here. Okay, so let's say we have carbon monoxide, 2 atoms, or no, 2 ATM, 25 degrees Celsius, and CO2, 1 ATM, 25 degrees Celsius. Indicate whether the RMS speed of the CO2 is greater than, equal to, or less than the average kinetic energy of the CO molecules justify. Okay. So when you see the RMS speed, I believe that's going to be in joules, if I'm not mistaken. Okay, so first we can, okay, so here's what we want to do. If we look at M1 and M2, that should give us an idea of the proportion of VRMS to one another, and we can justify it based on that. So to get my M, which is just moles, I'll plug both values into PV equals nRT. So pressure, you said, okay, let me just move this to this. Okay. So for CO, let's find the number of moles. P, our pressure, is 2. V is not given. So, okay. Yeah, I was going to say. Okay, so 2 times 1 equals n 0.08201 T. We have to get that in Kelvin. So 273.15 plus 25 is 298.15. Alright, just give me a second to pull my calculator out. Okay, so 2 equals 0.08201 times 298.15. This is 24.45. Solving for n, we get that we have 0.0818 moles of CO. Now for our carbon dioxide, so again, we need to find the amount of moles. Okay, so again, just plugging everything in. This is just 1 equals N R T. Alright, and so doing that, we end up with 0.0409 moles of CO2. Okay, so we have the amount of moles of each. And this problem isn't asking us to find the RMS speed of both, but it's, yeah, okay, no, that's fine. It's not asking us to find the RMS speed of both. It's asking for a comparison. It's saying, is the RMS speed of CO or CO2 greater? And so what we can do is we can actually plug this into Graham's law, which is m1 over m2 equals V RMS 2 over V RMS 1. Alright, so let's actually do this left-hand side. So my m1 will say CO is 1. So m1 0.0818 over m2 0.0409 square root. Okay, so doing that, this is going to come out to the square root of 2, approximately. Okay, so what this is saying is that V RMS 2 over V RMS 1 equals the square root of 2. Now, we don't actually know, can we use number of moles for the masses? Do you mean by here? Like this? Because M1 and M2 here, if I'm not mistaken, are... Oh, wait, that's molar mass. I apologize. I thought it was number of moles for some reason. Okay. So yeah, this was completely unnecessary. Although I'm not sure why it worked out so nicely. Okay. So in this problem, what you have to do is put the molar mass. Let's find M1, let's find M2, and then we'll sort of go back to what we were doing. I apologize for the confusion. We're doing something in my current chemistry class that's a little bit different, so I got a little mixed up. Okay, so CO2, we'll say CO is our first one, plus O will be accurate here. And this is going to come out to 28. Alright, M2, and then here we're just adding another oxygen. I'll just round it to 16 for this one. A lot of times you want to use 15.999, but in this case, it's not really imperative that we be super accurate, so I'm just using 16 for time's sake. Okay, so now we can do M1 over M2, just 28 over 44. So 28 over 44 square root is going to come out to 0.798. So what this is saying is that VRMS2 over VRMS1 equals 0.798. So let's think about this. This means that VRMS2 must be less than VRMS1. Okay? And if that's not immediately clear to you, we can cross multiply. and see that V RMS1 or that V RMS2 is going to be equal to V RMS1 times 0.78. And so from here we can say that V RMS2 is bigger, or is bigger, so the root mean square speed of carbon dioxide is higher than that of carbon monoxide. Okay, so hopefully that made sense to you. I apologize for the earlier confusion. But we can sort of move on. Yeah, kinetic energy 1/2 mv squared. I believe that's what it turned out to be. So VRMS2, yes. Let me know if that conflicts with what you're getting. Okay, so yeah, moving on. Here it's just important to know that our mass is in kilograms. Wait, hold on. No, okay. No, so VRMS1 has to be bigger because for every... This is sort of a weird way of doing it. I can just do it, write it out like this. 1 over this. So yeah. Okay. So there you go. So it turns out that carbon monoxide has the faster VRMS speed. And so so let's sort of think about why that's the case. And it all has to do with molar mass. I think that's how that is. And so basically this one has a lower molar mass, so it's going to move through faster when compared to carbon dioxide, which has a higher molar mass. Okay? So yeah, carbon monoxide has the higher root mean squared speed. Okay. So yeah, like I said, the mass here is in kilograms as opposed to everything else you've ever done in AP chemistry where the mass is in grams. So just keep that in mind. Unlike a lot of things in chemistry where you can sort of figure out the units on your own, this one it's not so easy just because a joule is like equal to something really weird. Like it's like, what's it, meters per second squared times kilograms. And unless you knew that, you wouldn't be able to figure out that this was in kilograms. So do memorize that. Alright, and then we talked about real gases versus ideal gases. And this sort of goes back to the postulates made above, and it's sort of discrediting 3 and 4 and saying, well, wait a second, this volume isn't neglected, and we shouldn't neglect the forces between atoms. And like I said, normally that assumption is only slightly inaccurate, but if a gas is cooled, so low temperature, or compressed, high pressure, now our assumptions do make a difference. And so these van der Waals equations give us a better representation for gases in this state. And I mentioned this in the video, you don't have to memorize this, but you do need to know that A is representing the force or the strength of the attractive forces, and B is representing the size of the atoms. And then I also mentioned this. If we plug in A equals 0, meaning no attractive forces, B equals 0, no volume, we get something very familiar, the ideal gas law. So these are the ideal assumptions. Alright, we also talked about IMFs. So we said that they're stronger as atoms get closer together. We just went over. And all of these forces that will be mentioned, or that are mentioned in the video, are also called van der Waals forces. So van der Waals forces equals IMFs. Dipole-dipole forces. This is where we have two dipoles in a polar molecule, and these dipoles attract each other. Alright, and then we talked about London dispersion. And this one isn't, I would think, is the hardest one to conceptualize. So if you guys have questions about the actual forces themselves or concepts relating to them, feel free to ask away. So what I wanted to go over was this polarizability. And so if we have something, let's say we have an atom with, I'll draw 15 electrons. This is going to be much more polarizable than something that only has 2. So let's take, for example, that this gets polarized. Okay, so I'll draw another one. If this one gets polarized, this one will as well. And here we'll say we have a force of +2. Here we have one of -2. On this side, we have a force like so. So we can see that these electrons are much stronger over here. And so not only does that make it more polarizable, meaning that it's going to sort of push electrons more, but the actual London forces in relating to that atom or compound are going to be much stronger. And then just note that these are instantaneous. They're said to last for an instant of time, and then everything sort of goes back to normal. Okay, hydrogen bonds. These are just sort of special dipole-dipoles. essentially the dipoles here are so strong that they warrant their own force. And the reason they're so strong is because hydrogen isn't very electronegative, and so atoms are essentially able to steal more electrons from hydrogen. Question is, what types of questions do they ask about London dispersion forces? So they might ask you okay, hold on, I'll go back. Okay, so they might ask you a question like this. What has stronger London dispersion forces? Iodine or bromine? So this is a really common one. And the real question here is, what does the electron situation look like? So yeah, exactly. So the one with more electrons is going to have stronger London dispersion forces. They might ask you about relative strength in an atom, so they might, this is the one that always comes to mind, but they might give you like, okay, in H2O, what is the dominant IMF? And it'd be like A, hydrogen bonding, B, London dispersion. And here you would need to know that if an atom has hydrogen bonding, that's going to be much more strong than the London dispersion forces that happen in that atom. So also note that it's important to know that London dispersion happens in all atoms. The same can't be said of dipole-dipole or hydrogen bonding, but in all atoms we have London dispersion forces. It's just that in something like H2O, these hydrogen bonds are much more powerful and much stronger, so we don't normally care about the London dispersion forces. Alright, and so you also, so you also asked about what has hydrogen bonding. And the simple answer is that if you have a covalent compound that has something bonding to hydrogen, you can pretty much bet that it has hydrogen bonding. So take, for example, like H2S, because I have sulfur, which is pretty electronegative, that's going to have hydrogen bonding. Okay. But the thing about it is, these are the ones that have it the most common. I'm thinking about it, and what really matters is the electronegativity and certain factors that they're not going to ask you about in AP chemistry. And so the rule to memorize is NOF. If something has O bonded with hydrogen, something is F bonded with hydrogen, or something is N bonded with hydrogen, these hydrogen bonds, or these are hydrogen bonds. If you see something covalent that isn't NO or F, you shouldn't assume it hydrogen bonds. So discount what I said previously. NOF is what you need to remember. Stronger London dispersion forces is not based on valence electrons, but total electrons. You're right in that sense that it's not based on the valence count, but what's really important in a lot of these hydrogen bonds is that, or I'm sorry, in these London forces, is that many of the electrons are sort of further away from the nucleus. But in a strict sense, valence electrons don't matter like the way they do in, say, chemical bonding. So to answer your question, don't worry about valence electrons when it comes to London dispersion. It's just a matter of total number of electrons. Okay, and then I asked if an atom has stronger IMFs, would its boiling point be higher or lower? We can go over that one now if you guys want, but the video coming out tomorrow will discuss that. Otherwise, if you guys don't have any more questions thus far, I can just sort of do some random stuff. So let me know what you think. Alright, so your answer is higher. Stronger IMFs, higher boiling point. And you're correct. If you're sort of looking for an explanation, the reason is that for something to be boiled off, you have to sort of break the IMFs so that something can sort of be free. And so if you have strong IMFs, we'll do double arrows. It's going to take more energy to boil something off that has weaker IMFs, because it takes more energy to break this strong IMF than this weak one and sort of boil it off to a gas. Yeah, so nice job. Yeah, if you guys have any more questions, let me know. Otherwise, I can do some practice problems that I have with me. So, yeah, if you guys have them, let me know. Otherwise, we'll just do some practice problems. Okay. No, you're good. Don't worry about it. So here's the question. Okay. Which of the following won't form hydrogen bonds. CH2F, C8H17OH, C6H12O6, NH4, or C3H5. Alright, so let me know what you think won't form a hydrogen bond of the list that I've given you. Okay, so if you guys aren't sure, let's remember NOF, or you can also say FON. Okay, your wild guess NH4 is incorrect. So the general rule to follow with hydrogen bonding in AP chemistry is NOF. If you have N bonded to H, hydrogen bonds. If you have O bonded to H, hydrogen bond. If you have F bonded to H, hydrogen bonds. But otherwise, you should assume that there's not a hydrogen bond. So let's go through the list and see what does and what doesn't have N, O, or F. CH2F, that's got F in it, so we can cross that out. C8H17OH, we have an O in there, so we can cross that out. C6H12O6 has an O, so we can cross that one out. NH4 has N, cross that out. And C3H5 does not have N, does not have O, and does not have F. So we can say that that's our answer. That's the only one without N, O, or F in it. So I can say that's my answer. In a more complicated problem, or maybe challenging, they might give you something. They might give you something that has, everything has N, O, or F, and it's up to you to draw the right Lewis structures and say, oh, in this case, my hydrogen isn't actually bonded to N, O, or F, and so it doesn't have hydrogen bonds. But in this one, you can sort of safely assume that these are all, that these hydrogens, at least one of them is bonded to an N, O, or F that occurs in the compound. Alright, so let me know if you guys have questions on that. Hopefully that sort of cleared up any confusion you might have had. Okay. Let's see, what else can we do? Okay. Let me just get some more white space here, and then I will give you guys the next practice problem. Unless you guys have questions, again, feel free. which of the following is the most polarizable? Br, Na, I'm sorry, Ca, Ne minus, ooh, and S. Alright, so let me know what you guys think, and I'll give you the answer in just a second. Alright, so our answer here is our first compound, Br. So let's sort of jump in and see why that's the case. First thing we should do is let's actually write out how many electrons each has. So bromine is the atomic number 35. Calcium is atomic number, hold on a second. Calcium is our atomic number 20, so we have 20 electrons. Neon, atomic number is 10, but we're Ne minus, so this has 11. And sulfur is atomic number 16, so we have 16 electrons. Okay, so if we think about polarizability, that's total number of electrons. So essentially we just want to pick the one with the highest number of electrons, Br. Alright, we're in sort of the last 5 minutes or so, so if you guys have questions, let me know. Otherwise, I can just sort of yak a little more. Okay. C30, H62 is solid at room temperature. Why is this if the compound is nonpolar? Okay, so we want to think about C30H62. We're saying it's solid at room temperature, and I'm trying to get at why is this the case if the compound is nonpolar? Well, so if it's nonpolar, we can immediately say that these aren't present in the compound. So our only IMFs are London dispersion. Looking at our formula, we have a large compound with a bunch of electrons. So it's going to be very polarizable. And so we're going to have very strong London dispersion forces. That's the explanation. Alright, so I'll give you guys a little bit, if you have questions on that, or just sort of anything in general, let me know. Alright, seeing that we don't have any more questions, should about wrap up this week's live stream. Thank you everybody for watching, and everybody have a good week.